Those of you who follow these webinars chronologically may remember that at the end of last week's webinar I was hesitating whether I would be available this week for a live stream, and indeed, as I suspected back then, that is not the case. So once again, this webinar is pre-recorded on Sunday evening. And as usual then, so should you still have questions, please give them via the forum or via Zulip, and I will deal with them next week. So this is the feedback webinar about the chemical bond topic. But first, some administration and computational things regarding the project. The project teams who had started are still going fine, I see from their reports. Unfortunately, I didn't get to the point of giving feedback on the intermediate reports that have been submitted. I will try hard to do that in the first half of the coming week, but it didn't happen yet. Sorry for that. Then this is a good time to give you some calculation hints about all kinds of things that technically could go wrong or can be improved in your Quantum Espresso calculations. This is partly based on questions you have submitted during the past week and partly on questions that appeared during the past years, but that nevertheless may be useful for you as well. So let's go through that. Somebody asked, could I save some time by starting a new calculation from the output of a previous one? Say you have calculated an energy at a given lattice parameter, and now you slightly change the lattice parameter and you want the energy for the new lattice parameter. Do you have to start from the very beginning again, or can you reuse part of the information in your previous calculation? Well, the answer is yes, if the difference is not too large, so you don't use a totally different lattice parameter or even a different crystal structure, so then it would not work. But if it is only a few percent change, then you can save time by putting in the electrons block that you want to start not from scratch, not from free atom information, but from information that is available in files that have been saved at the end of the previous calculation. So this only works if you don't change the prefix value. If the prefix still keeps being the same as in your previous calculation, then it will read files with that prefix and with information on the potential and the wave function, and you will start from the final point of your previous calculation rather than from a superposition of free atoms. Then a related question, is it possible to stop a calculation or to pause it in some way and then resume it later? And this is possible if you make a file in your folder that has the same prefix value as your running calculation and then .exit with capitals at the end of the file name. If that file is present, then your calculation will stop in a clean way once it reaches the next electronic iteration. And if you then later use in the control block restart mode equals restart, and with using exactly the same pw.x command, then you can continue that calculation at exactly the same point where you had stopped it. We met in this module also magnetic calculations, so how, and I will come to that more specifically later on, But how do you run technically a magnetic or a spin polarized calculation where you do not always have the same number of spin up compared to spin down electrons? You have to specify in the systems block the keyword n-spin equals 2, and you have to give for at least one atom in your structure, but usually for more of them, you have to give a starting magnetization. So this 1.0 means atom number 1 in my structure has the maximal amount of more spin up than spin down electrons. And the same for atom number 2 and so on. If you use n-spin equals 2, then you will see extra information in your output file. You will see the magnetic moment per atom, which is the difference between the number of spin up and spin down electrons. Every difference of 1 gives you 1 Bohr magneton of magnetic moment. So in this case here, atom number 1 in my structure has 2.02 Bohr magneton of magnetic moment. And you have this value also per unit cell. If you try cases that are a bit more difficult, that have more electrons in the unit cell, then you may run out of memory. And that is shown in the virtual machine by a silly killed message. Now, if that happens, you can first inspect at the beginning of your output file, somewhere in the first few 100 lines, there is this estimated total dynamical RAM. And that tells you what is the amount of memory that calculation is expected to need. Then you can close your Quantum Mobile, but still with VirtualBox running. And in VirtualBox you choose Settings. In the window that then opens, you choose System and the first tab Motherboard. And there you have a slider by which you can choose the amount of memory that is available for the virtual machine. That can of course never be larger than the amount of memory that your laptop physically has, but by default this is at a rather small value, so probably you will have some room to increase that value. And once that is done, you start Quantum Mobile again, and now your case can use more memory. So that can prevent that killed message, unless your unit cell is really too large, has too many atoms, or you use a basis set that is too demanding for your computer. So you can, if you need that amount of memory to do the calculation, and your computer cannot offer that amount of memory, then you should move to a different computer. Good, so these were some calculation hints that I hope at this stage can get you past some problems, some technical problems that you may encounter. And let's now move to the science, to the chemical bond, the topic of the past week. And where do we position this in the course? Well, last week I showed you this slide that summarizes much of the first few weeks of the course, where we examined if we give a particular crystal to a DFT code and we calculate the total energy of that crystal. How can we use that information? Well, we can use it to predict the equilibrium geometry, to predict some elastic moduli, to compose the phase diagram and make predictions about the existence of that particular crystal. All of that was possible based on total energy. Last week we looked at other properties that are beyond total energy. We could examine the band structure and the density of states. which will learn us whether a material is predicted to be a metal or an insulator, for instance. That was a feature that comes from condensed matter physics. In the past week, in the present module, you looked at another property, the electron density, which is a property that can answer some questions that are usually asked in chemistry. What is the chemical bond in a given crystal? Can we recognize what is the chemical bond based on features that density functional theory can compute for us? And chemical bond, that's not a quantitative number. This is not, you cannot tell that the chemical bond is that percentage covalent and that percentage ionic. This is always a rather qualitative measure. But, still, that qualitative information can be obtained from density functional theory. So, and therefore, we first started with a quick revision of something you very likely know. What are the common chemical bonds and how is this usually taught in chemistry textbooks or physics textbooks? And we associated some features to that. We said, for instance, that a covalently bond crystal is usually more brittle than, say, a metallically bond crystal. And there was a question a few years ago about some more details for this. Often the material science people, they know a bit more about brittleness. They can wonder about additional details. Also for the people working on the project this year, where ductility or non-ductility, often called brittleness, not really correctly, whether as the project is dealing with these topics, it can be interesting to look at brittleness or non-ductility in a bit more detail. So within the past week, the information in the course focused on non-ductility at the atomic scale. So we reasoned, if you have covalent bonds that are stronger in one direction than in another direction, then if you deform a crystal in a direction that is not consistent with these chemical bonds, then your crystal may more easily break. So that is predicting brittleness, non-ductility from the atomic point of view. But especially the material scientists among you will know that ductility also depends on features that play at a higher length scale, at the microstructure. You can have defects in a crystal, for instance, dislocations. This here is a cartoon of a dislocation. You have a cubic crystal lattice, and here at the left top, a half plane extra is inserted. So without this plane, this would be a perfect three-dimensional cubic lattice, but half of an infinite plane is inserted. And if you now would make bonds between these atoms and break bonds between these atoms, then you could get into this situation. And this basically means that your dislocation, your half plane, has moved a lattice parameter to the right. And if you continue this process, you can swipe your dislocation throughout the entire crystal until it reaches the right hand side. So you have basically skewed your crystal. It started from a crystal that had a bit extra atoms at the left hand side and they moved to the right hand side. That's a skew. You can look at brittleness, at non-ductility also this way, and this effect does play an important role. If dislocations can easily move in a certain crystal lattice, then this crystal will be ductile. You can deform it because the moving dislocations will give way. If these dislocations do not move very easily or do not move easily in a given direction, then the crystal will break instead. It will be non-ductile. So that too, that microstructure level with dislocations, defects at the microstructure level, this too is a factor that can affect ductility. That is a bit harder to predict from DFT. It requires calculations for larger unit cells, something of the size you see here, but in principle this can be done. After this overview of chemical bonds, you looked at cohesive energy. What is cohesive energy? And you made an exercise about this. Free atoms of sodium, free atoms of chlorine, a teaspoon of each. You bring them together and you have a teaspoon of rock salt. If you do this in a particular lab room, how will the temperature of the room react on that? Which is a way of asking how much energy has been released by that chemical reaction. I asked you to calculate that temperature rise, and there were quite a range of values. Something barely noticeable, 0.065 degrees, up to 60 degrees. But most of the answers centering around the order of magnitude of 1 degree. Well, this was an exercise where you have to make several assumptions, so there is not one unique correct answer. Depending on the assumptions, well, I agree that you end up somewhere in that ballpark of 1 to 3 degrees. And you could see one example of a full reasoning. After having submitted that answer, you had the possibility to download a file with the correct reasoning. So in case you missed that, you can still go back there and see what an example of a correct reasoning was. Somebody wondered, what is the difference between the cohesive energy that we defined now this week and the formation energy that was discussed in the context of the phase diagram? These are very related topics, but they are indeed not the same. And the difference is easily explained. Cohesive energy, that's the energy difference between a crystal, say rock salt, sodium chloride, and the atoms that make that crystal, but as free atoms. So free sodium atoms, free chlorine atoms. The energy difference between these two situations, that is the cohesive energy. Whereas the formation energy, that's the energy distance between the same crystal and now these elements that make the crystal, but in their elemental ground state. So you take solid sodium, an unary sodium crystal, and chlorine gas with Cl2 molecules. So the energy that is represented by these atoms and the difference between that situation and the rock salt crystal. That is the formation energy. So the formation energy will always be smaller than the cohesive energy, because first you gain energy by combining the free atoms into the elementary crystals, and if you then still can react these to make, say, this diatomic crystal, then you reduce the energy even a bit further. So cohesive energy is with respect to free atoms, formation energy is with respect to elementary phases. Why do we study cohesive energy? Because it is a property that can give us one indication about the type of chemical bond. By calculating the cohesive energy, you will be able to eliminate at least part of the possibilities. The charge density difference plot, that will be another more visual way to distinguish between the types of chemical bonds. And first, for the cohesive energy, there you have to you calculate the energy of the crystal, that you already know how to do that, but you need to compare that with the energy of the free atoms. And that is a new way of reasoning that was not for everybody equally clear. So I gave you this set of input files for single atom calculations, and either you accept that these are input files for a single atom calculation, you run the calculation and done, and then you will not wonder what this was, or you will look at that input file and see what it represents, and then you see, these are just FCC cells. So how is that a single atom calculation? Well, this is something that we will see in more detail in a few weeks, but I can tell this already here. If you would visualize that input file, you would see you have the primitive cell of an FCC crystal, but with a very large distance between the atoms. If you measure the distance between these two atoms in X-cris, then you have something more than 10 angstroms. That therefore means that this is a trick to mimic a free atom in a code that is meant to deal with crystals. Quantum Espresso needs unit cells. If you don't have a unit cell, you have no way to start the calculation. So how can you use a unit cell and nevertheless do a free atom calculation? Well, make the lattice parameter of that unit cell very large, such that the atoms do not interact with each other anymore, and they are essentially isolated. There are some other reasons why to do that, particularly with an FCC cell, because there you have the largest number of neighbors, nearest neighbors, and although they are far away, you still have 12 nearest neighbors in a rather isotropic surrounding. So the FCC cell is quite ideal to mimic an isotropic surrounding. It should be one atom in empty space. In reality, it's one atom with 12 nearest neighbors far away. And that is better than one atom with, say, 6 nearest neighbors far away, because these 6 nearest neighbors, they still have some direction information, some spurious direction information, and by averaging this over 12 nearest neighbors in all directions, you have less noise due to these distant nearest neighbors. Somebody made the comment that if you try to download these CIF files, that doesn't succeed, and indeed I checked it, and also for me it doesn't succeed anymore, and this turns out to be due to safety settings in browsers, Chrome in my example, and apparently browsers do not so easily anymore allow you to download these files. There is a way around, and I have now added the hint that you see here in yellow. I have added that in the core site. If you just copy the link, then go to a new tab, paste the link there, then it will try to download the file, the CIF file, in that new tab, but it will ask you the question, this seems to be an unsafe download, do you really want to do it? And if you then answer yes, then it will put the file in your download folder. it doesn't ask you that question when you click on it from within the course site. Okay, so you have these, you have downloaded these FCC unit cells that are essentially for free atoms, and wait, what was this question again? Let me read it. Related to the cohesive energies, I felt I could reproduce the crystal-based input files, but not quite those for the single atom calculations. And I'm not sure whether I encountered single atom calculations in the course yet, so how are we dealing with single atoms? Well, exactly in this way, by these artificial FCC cells that have this artificially large lattice parameter and therefore nearest neighbors at a long distance. Somebody noticed that in these FCC cells for single atoms, that the n spin was set to 2, so you do a magnetic calculation, whereas for the crystal, there you don't do the magnetic calculation. So why is that needed? And someone else gave an even more specific question. So the question goes like this: you turn on spin polarization, you turn on magnetization in these single atom calculations, and the spin of the atoms, the spin of these atoms, the magnetic moment, is in the z direction, but single atoms, they are isotropic in space. So why do you have then a magnetic moment in the z direction? Well, what is the answer to these two questions? First, why do you need a spin polarized calculation for single atoms and not for the crystal? Look as one of the many possible examples to the carbon atom. If you look at the position of the carbon atom in the periodic table, you have a complete 2s shell, and you start filling the 2p shell. And you have only 2 electrons in the 2p shell. So if you apply Hund's rules, these will be 2 electrons with the same spin, so twice, say, spin up and never spin down. So you will have a magnetic moment equivalent to twice the magnetic moment of a single electron, so 2 Bohr magnetons, for the spin moment alone. However, if you would put carbon in a crystal, graphite or diamond, that is not magnetic. So in the crystal, the carbon atoms have lost their magnetization. The electrons will be equally distributed, up and down will be equally distributed over the crystal orbitals. But in the atomic orbitals, the way the atomic orbitals are filled, following Hund's rules, they are not equally distributed. So all atoms, all elements as a free atom have a magnetic moment, except the ones with fully occupied shells. And say magnesium will not have an atomic magnetic moment, cadmium will not have an atomic magnetic moment, same for xenon, but everything else that has not a filled shell will have a magnetic moment. So because you know that this will happen, and because that situation will have a lower energy than the situation without a magnetic moment, otherwise you wouldn't create a magnetic moment if the energy would not be lower. So because you know that this will lower the energy, well, in order to calculate a reliable cohesive energy, you have to take the ground state of the atom, so with the magnetic moment. Now, how can this be reconciled with the fact that a free atom is isotropic and that therefore there is no preferential access, whereas if you look in the input file, you will see the moments are somehow related to the z direction. You measure the components of the moment with respect to some z direction. This is an artifact because we are essentially solving Schrödinger's equation and not the fully relativistic Dirac equation. In Schrödinger's equation, there magnetization is not naturally present. You can introduce it by solving the Schrödinger equation for spin up and spin down separately and then couple these two results. And in that process, you introduce an arbitrary z-axis in order to express the z component of the spin. In the Dirac equation, that would not be required. Their spin emerges spontaneously, and also magnetic moments of atoms will emerge spontaneously. But DFT is in most codes Schrödinger equation based, so you have this artificial z-axis that has not really a physical meaning, especially not for a free atom. If you introduce a crystal where the isotropy of space is broken, there you can ask the question, where is my z-axis pointing? Now, still, even there, if you don't introduce spin-orbit coupling in your calculations, then the answer to that question does not matter. Your z-axis is not really defined, but with spin-orbit coupling, which couples the lattice and spin degrees of freedom, there you will be sensitive to your choice of z-axis. It's not something we will meet in this course, but for more advanced DFT calculations with spin-orbit coupling, that is an issue to consider. So I hope that this answers these questions about spin. Now, if you then did the calculations for the free atoms and for these 4 crystals, FCC aluminum, FCC argon, germanium and sodium chloride, and you calculate the cohesive energy per atom, you should have found numbers more or less as here in the last column. And what does that tell you? Well, if the cohesive energy is very small, around 0, that is a crystal that is van der Waals bond. That doesn't have ionic, covalent or metallic bonds. No, it's a van der Waals bond. Not surprisingly, this happens for this noble gas crystal FCC argon that can exist only at very, very low temperature because normally argon is a gas. So calculating the cohesive energy is a way to find out at least what is van der Waals bond and what is not van der Waals bond. Somebody asked here, when you calculate the total energy of the crystal, should you do a geometry optimization for that total energy, or can you just work with the experimental lattice parameters and atomic positions? Well, there I would refer back to our iron aluminum example. We have seen that if you do the proper geometry optimization, you lower the energy. And unless your DFT prediction for the optimal structure would be really spot on your experimental value, unless that would happen, it means that if you would take the experimental geometry and then calculate the energy, and then optimize the geometry and calculate the energy again, in that second case the energy will be lower. Maybe not a lot, but definitely lower. So therefore, a pure DFT prediction where you try to take into account as little experimental information as possible there you should start from the lowest energy structure that you can achieve, so that means the geometry optimized structure. If you do not geometry optimize, then your numbers, your cohesive energies will be a little too small, because you can still lower the energy by geometry optimizing. And then, you could wonder, if I take that experiment, my cohesive energy will be a bit smaller. If I take another, it will be even more smaller. So your prediction would depend on experimental information. So the cleanest number that at least does not depend on experiment is one where you use the DFT optimized geometry. So my answer to this question would be yes, preferably yes. So with the cohesive energy we can identify the van der Waals bonding, but we still have to differentiate between these other types of chemical bond, and that can be done based on the charge density difference. So we calculate the charge density, the electron density or the charge density of the crystal. We subtract the charge densities of the free atoms, and we look to the regions of space where electrons move to. So in this color code here, the bluish regions are the ones where there are less electrons in the crystal than in the free atom. The magenta regions are regions where there are more electrons in the crystal than in the free atom. So the magenta regions are the regions where the electrons from the atom moved to in order to form the crystal. And with FCC aluminum, you can see that these magenta regions are rather uniformly spread across the region in between the atoms. And that is typical for a metallic bond. It's very different if you take a crystal like germanium, where we know that this is covalently bond. The magenta regions are now located in between lines, that halfway between lines that connect two atoms. So there is electron accumulation in particular regions. The chemical bond is stronger in particular regions. That is typical for a covalently bond crystal. And if we have an ionically bond crystal, here we get extra electrons around a particular atom. So not in the interstitial region, but centered at the location of particular atoms. So that is typical for an ionic bond. While making this picture, so I showed you in the Let's Play section the procedure how to make such pictures yourself with Quantum Espresso, then you could run across the problem that you have these nice pictures from XCRISDEN, and then you have to click a button to start a modification in the display or whatever, and that button is not on your screen. If that happens, then take the settings from your Quantum Mobile, displays, resolution, and then change the resolution of your Quantum Mobile on your computer, and then you will, if you choose the right value, you can try a few of them. If you choose the right value, then the entire window will be visible on your screen. A few years ago, somebody wondered, how is that charge density calculated with Quantum Espresso and XCRISDEN? Because I never have to do a free atom calculation. I didn't have to use these FCC type of cells. And yes, that's a valid question to wonder about, and maybe some of you have wondered about it in the past week as well. The answer is that when you go through that procedure, when you use these post-processing routines of Quantum Espresso to display the charge density, then it will calculate internally the charge density of free atoms, but not with a supercell, not with such artificial FCC lattices, but with a module that really can treat free atoms for real. So there is no periodic boundary condition, just a free atom calculation directly for the free atom. And then it will put these free atom densities on a lattice that coincides with your crystal, such that it has a superposition of free atom densities, and it makes a crystalline density out of that. And it's this crystalline density that is then subtracted from the charge density of the actual crystal. So you don't have to do explicitly the free atom calculation. It's done automatically. And in an even better way, in a more direct way than with the FCC crystals that we used before. This was then the point where this old puzzle about the ionic bond in rock salt and how you can better understand that ionic bond, when this puzzle could be tackled. And I had asked you long ago, several weeks ago, at a moment when you were not yet biased by this explanation here, I asked you, how do you imagine the ionic bond in rock salt? And these are a few of the pictures you submitted, where, as in many textbooks, you see that you take one electron away from sodium, you give it to chlorine, and therefore you get a positive sodium ion, a negative chlorine ion, and they electrostatically attract each other, and that lowers the energy. This is indeed the case how the ionic bond is often explained, but you saw then in one of the videos of the past week that this is not the case, that the better picture is that you have a sodium atom with an electron that is at quite a distance away on average, and that distance is more or less the distance where the chlorine atom sits. So the way how these two atoms bind is not by transferring one electron, but rather by a key and lock system. And they lock to each other at that distance because the chlorine wants to be at a position where that lone electron of sodium is. So this is a chemically better justified way to imagine an ionic bond. And you can get that understanding directly from analyzing these cartoon pictures, and by comparing that with the charge density difference as you have calculated for rock salt. So remember the picture for rock salt where the magenta region was around the chlorine atom. And so in this picture, this is not because electrons have been transferred from sodium to chlorine, but because these extra electrons were already present at around that distance, and therefore in the crystal, there are extra electrons at the chlorine position compared to if there would have been a free chlorine atom there. And if you generalize this to a cartoon that would better describe the actual rock salt binding, it would be something like this. And so the extra electrons of the sodium, they are at the chlorine positions without a transfer. And this we use then in a last step to look at crystalline bonds in the same way as we look at atoms. So in atoms we fill the atomic orbitals. In crystals we fill the crystal orbitals. And here I have to emphasize that what was shown in that video is not something that was explained with Quantum Espresso. That was done with a different DFT code where that procedure was a bit more convenient. You can do the same with Quantum Espresso, but it's not straightforward. So don't bother about how can I reproduce that. And it's not a goal, a direct goal in this course to be able to reproduce that. But it's a goal to have an understanding of what is a crystal orbital. And here you saw a crystal orbital. And let me add one more picture to this, and so one more way to visualize this. So you have here isosurfaces for a given crystal orbital, one that corresponds with the quantum numbers as indicated here in this band structure. So this K vector here at gamma with a particular band index. So that is the orbital characterized by these quantum numbers. And now, because you have to plot that in a three-dimensional picture, you plot an ISO value for that orbital and you get this picture here. Well, that would be an example of an orbital that overlaps many nuclei. So an orbital in an atom that is centered around one nucleus, but you see here in this picture that the orbital in the unit cell is at many different places. So in a cartoon it would be like here at the right hand side. You have an orbital that has a probability to have a certain electron density at many places in the crystal. In contrast to deeper orbitals in the crystal, so if we would plot the same type of isosurface picture for, say, the 1s orbital in sodium, then you would see that there would be spheres around all the sodium atoms. And you could imagine this as there is a sodium atom with this orbital for one set of quantum numbers. For another set of quantum numbers, I have another orbital and another one. So all identical orbitals, all centered around an atom, all non-zero around a particular atom only, whereas the crystalline orbitals that are involved in the chemical bond, they are non-zero everywhere. So I hope that this image helps a bit better to imagine what a crystal orbital really is. And with this we have reached the end of this rather short feedback webinar. So let's have a quick look on what we will do next week. We had already a week with something condensed matter physics related. Now we just had a week with something more chemistry related. Next week is spent to a topic that is more in the realm of materials engineering, elasticity and elastic moduli. And that's also for the project, the people working on the project, that's a very relevant week. Okay, well, you know the drill. As this is pre-recorded, I ask you to write your summary and formulate your exam question after having stopped this video. And I didn't yet upload the ones that were contributed 1 and 2 weeks ago. I will do this certainly long before the exam, no worries. So please continue adding your contributions. You will see them appearing in the course site in due course. So let's jump over this, and so there will indeed no questions here because this is not live. And as far as I can see now, next week will be live again. So should there be any questions throughout the week, put them on Zulip, put them on the question forum, or email me if it is urgent. And otherwise, we'll see each other next week in the webinar. Bye bye.